So let me tell you the plan today. So again, welcome. Well, let me share my desktop so we can see what's going on. So the plan today is we will start out by going over the exam. So you took the exam, I'm sure you all know that. And it's been graded. I took a look at it. A lot of things to talk about and go over the exam. Then I'm going to spend a little bit of time, not a lot of time, just a tiny bit of time talking about the application presentations. They're going to happen in a few weeks. And then we're going to get on to the next big phase of this class. As I mentioned before, this class is really two parts. This could just as well be taught as two separate 6-week classes because one has nothing to do at all with the other one. So what we're doing today is we're doing just the beginnings of it. And just about everything we're doing, all but one little tiny thing, is done in pre-calculus. This will be a review, but that doesn't mean you remember everything. And it's definitely not one of the easier things. So we'll start with explicit and recursive sequences. So today's all about sequences, by the way. And then we'll talk about the limit of a sequence. Then we'll look at the relationship between limit sequences and functions. And then we'll look at how limits change based on algebra, what you can do. And then we're going to have the squeeze theorem for limits. So it's the same squeeze theorem for limits that you had in first quarter calculus, but now it's for limits of sequences instead of limits of regular old functions. And then we'll get into bounded sequences. So what does it mean for a sequence to be bounded? And then finally, we'll get into the monotonic sequence and the monotone convergence sequence theorem for sequences. So that is the plan of the day. Are there any questions before I jump into the exam and talk about it? As I mentioned, there's no quiz today. So if you expected one, you're not getting one because nothing to quiz you on. Because if you remember the last time we met, that was in, all we did was review for the test. We didn't do new material, so there's nothing to quiz you on. But that will change. Wednesday, the quiz comes back. So, which is a good thing because you guys seem to like the quizzes. And, but are there any questions at all? Anything you have that you might wonder about? Okay, I want to mention one more thing in the calendar. I'll mention again. Normally, I tell you, if you come to the college and go to the class next Monday, they'll arrest you. But actually, that's true of any day. But the point is that next Monday, we don't have class. And hopefully, you all know why. Anyone know why? Yeah, for Memorial Day weekend. And again, doesn't matter whether we're in this, Eve-based online class or a regular face-to-face class. Holidays are holidays. So there is no class on a week from today. 8:30 in the morning. I don't know. I might be waking up in a tent, depending on that. So again, I might not be around much if you have email questions on the weekend also, because I'm going to actually enjoy the weekend, and hopefully you will too. So that is just one note, is that for the calendar, next week is a holiday, and it's still a holiday, even though it feels everything's so weird. But I'm just going to respect the holiday. Okay, let's talk about the exam. And as you might guess, everyone got the first question right. All you had to do is write your name, so I'm not going to spend time on that one. But I do want you to please ask any questions as I go through this. I'm going to go through kind of fast because the idea isn't for me to just take the whole exam in front of you, because you've already done that. And I want to make sure you guys got to look at my comments that I wrote. You able to see them and everything? At least I hope so, because I wrote over 20 pages of comments total, probably more like 40 pages. It took a very long time. You'll notice that this test wasn't graded until Sunday. That's because I was grading all weekend until Sunday morning, and then I was done. But it's not like a regular written test. It's just much more difficult. And I had to write lots of comments because I can't just circle something and cross it out. I have to write a whole sentence on what happened. So take a look at my comments because that will help you guide you towards what went wrong. Even though from now on, we don't use anything that we did on this test, the final exam will cover this test, okay? And so might the applications. So let's go through this first limit. So the first thing is prove or disprove the limit exists. If it exists, find it. So the first thing I like to do with limits is I say, well, let's just try some easy ones. If x and y are both 0, it's clearly 0 over 0. Okay, stop me if you don't understand something I said. If x is 0, then the numerator is 0 and the denominator is y to the 4th, and that just gives you a 0. Because remember that until you take a limit, you don't have 0. Okay, if y is 0, you also get 0 in the numerator, and you don't have 0 in the denominator, so that's a 0. But if y equals x, everything changes, because then you get a power to the 4th on the top, and a polynomial to the 5th plus to the 4th on the bottom, and that actually is going to converge. So that means that we're going to try limits. So first I'm going to go like this. Whoa, what just happened? Didn't let me in. Will it let me? I didn't think so. All right, just a minute. That didn't work. All right, so if you take a limit, and I'll just do this by hand, limit as x approaches 0. And if we plug in y equals 0, so in other words, we're going to go along the x-axis, then you get 0 over x to the 5th. And I want to note this is y equals 0. Okay, some people had trouble with this. The limit as x approaches 0 of 0 over x to the 5th. What is that? Yeah, that is 0. Okay, it's not 0 over 0. That actually is 0. That is defined as 0 because remember, x is not 0. It's close to 0. And if you have 0 divided by something close to 0, it's just 0. Then choose, you could choose y equals x, or if you want x equals y equals t. Some people did it that way. There's a couple ways of writing it. And then we're going to have a limit as t goes to 0. And then the numerator now becomes t to the 4th, 2t to the 4th over, and the denominator is going to be t to the 5th plus t to the 4th. Any questions on that? Okay, notice I can cancel a t to the 4th. I can divide top and bottom by 2 to the 4th. And that gives me a limit, still t approaches 0, of 2 over t plus 1. And what is that equal to? That's 2. So since there two paths have different limits, the limit does not exist. Let's write D and E. Okay. Okay, these are two paths that both go towards the origin. Any questions on question 2 before I move on to 3? Okay, let's move on to number 3. Okay, number 3, again, prove or disprove the limit exists. Okay, if it exists, find it. So by the way, if you plug in 0 over 0, 0, you get 0 over 0. So that doesn't work. Okay, if you plug in x equals 0, then you get a 4y cubed over y squared, or 4y, that goes to 0. If you plug in y equals 0, you get 3x to the 4th, negative 3x to the 4th over x squared. That's negative 3x squared, and that goes to 0. If you try y equals x, you also get 0. If you try real quickly in your head, again, I'm not writing it out because that's the whole point. And they all go to the same place. Does that, if everything we tried in our head goes to the same place, is that a proof that the limit is 0? I mean, the limit is, yeah, is that a proof that the limit is 0 if everything we tried in our head goes to 0? Yeah, no. Trying 3 things is not enough. Trying 100 things is not enough. So there was only one way I showed you to prove the limit exists. And what was that? Yeah, it was polar coordinates. So we're going to take the limit as r approaches 0. That does not mean theta goes to 0. Theta isn't anything. Okay, that's for every theta. And we got to show the limit is equal to 0. So let's plug in. If r equals 0, then what do we get? Well, we have 4 r cubed times the cosine, sine cubed of theta minus 3r to the 4th times the cosine to the 4th of theta divided by, and x squared plus y squared is r squared. Any questions so far? Okay, let's divide by r squared. Just divide everything by r squared and you get the limit. I'll even copy and paste. As r goes to 0, we get 4r times the sine cubed. In fact, let me just, easiest is to copy and paste and get rid of the r squareds. So we get 4r times the sine cubed of theta plus minus 3r squared times the cosine to the 4th of theta. And r is going to 0. So one thing is that sine and cosine are continuous functions. So if you have a continuous function and r goes to 0, that means both of these go to 0, then the whole thing goes to 0. That's it. So therefore, the limit is 0. Any questions on number 3? Do you agree it's always easier to watch than to do? At least most people think so. But I didn't do anything tricky. These are very standard problems. Okay, that's why, you know, some of you did real well on them and some of you didn't. And again, these are very similar to the ones I did in the lecture. Okay, and that's what I try to do. Okay, and very similar to the quizzes too. Find the equation of the tangent plane to the point 201 on this surface. So how do you find the equation of a tangent plane? You need a point and you need a normal vector. The point is given. So how do we find the normal vector? In one, yeah, the gradient. Okay, so if we take grad of f, well, that's going to be equal to, that'll be 1 over 2 plus y, comma, x, comma, negative 10z. Any questions on that so far? Okay, then we're supposed to plug in the point, 2, 0, negative 1. So grad f of 2, comma, 0, comma, negative 1. And if you plug that in, notice y is 0, so that just gives you half for the very first coordinate. 1 over 2. And then for the second coordinate, we have x, and x is 2. And for the third coordinate, we have z is negative 1. So negative 10 times negative 1 is 10. Any questions on that? Okay, there's our normal vector. You always know the normal vector is orthogonal to a point on the plane. So that means that if we take the 1/2 to 10, I'll just copy it and paste it. And then we dot it with x minus 2, comma, y minus 0, I'll just write y, comma, z minus negative 1 or plus 1. We're supposed to get 0. So in particular, we can say 1/2 times x minus 2 plus 2y, and then plus 10 times z plus 1 is equal to 0. Okay. Now I just asked for the equation of the tangent plane. That's enough. Okay. I didn't say and then do more algebra. I have an equation. That's the tangent plane. Any questions at all on question 4? Okay. Question 5. Okay, a hiker is planning to climb Mount Partial. The altitude of the mountain can be modeled by this interesting function. And now there's an A, B, and a C. So if the hiker is at the point 2, 3 and wants to take a step in the direction of negative 1, 1, how steep will she be climbing, up or down? Explain both quantitatively and qualitatively. All right, what do we have in calculus that is the measure of how steep it is for one step? What is the measurement of how steep something is? Because we have that. It's a slope, but I'm looking for calculus stuff that we did this quarter that you hadn't ever heard of until this quarter. And it's not the level curve. The level curve is where you would walk if you don't want to go steep at all, up or down. Do you see? Yeah, it's a directional derivative. So we are asked to find du of f, or sorry, of a in this case. And du of a is equal to the gradient of a at the point. And the point, by the way, was 2, 3. Dotted with the unit vector. Now the unit vector, see, we have the vector negative 1, 1. We just got to make a unit vector that has magnitude 2. So it'll be 1 over sqrt of 2, 1 over the square root of 2 times negative 1, 1. Any questions so far? Okay, so that's how to get started. And a lot of you didn't like, I think you just didn't see that I'm asking for the directional derivative. But that's the whole point of the directional derivative. It tells you how steep it is. So now we just got to compute. We got to find the gradient of a. Well, that's not too bad. Okay, I tried not to give you anything that have like miserable calculus. And that's 2y minus 2x minus 10, comma. And then the second coordinate is going to be 2x minus 4y. Okay, now let's plug in. We'll plug in 2, 3. And again, so if x is 2 and y is 3, you get -8, comma, -8. Any questions on that? Okay, so now we just do the dot product. So let's go and do the dot product. And what we get is, let me just write it out. Well, I'm going to write 1 over square root of 2. That's just going to be there. And then times. So now we're going to take the dot product of -8, -8 with -1, 1. And that is what? It's a beautiful, easy dot product.
8, 8.
I'm looking for a dot product. Remember, the dot product is a number.
16.
It's not 16, so it's -8, -8 dotted with -1, 1. It's 0, right? -8 times -1 is 8. And then -8 times 1 is -8. 8 plus -8 is 0. So one of the nice things that square root of 2 just goes away. Okay, so what does that tell us? So I just did it quantitatively. Qualitatively, what can we say about that step that she's about to take? Does she need poles? Is she worried? No, it's flat. So the step is flat. Any questions on that? Okay, B. So B is, in what direction from the point 2, 3 must the hiker climb in order to experience the steepest possible step? So we had a theorem. In what direction will make it the steepest? In one word? For any differential function. Yeah, the gradient. So notice that it's a direction of -8, comma, -8, because that's the gradient. And by the way, that means you're going down and left or southwest. Because on a map, that would be southwest. Any questions on that? Okay, now what is the peak and how high is it? Okay, how do you find what the peak is? In calculus, what's another way of saying it? Yeah, we're looking for the maximum. We're looking for the maximum. And the way you find the maximum is you take the gradient, you set it equal to 0. So to do that, we've already taken the gradient. That was and not at the point, but just general gradient because we're looking for a point. So that means 2x minus 2y minus 2x minus 10 is equal to 0. And 2x minus 4y equals 0. Okay, I think the second equation is easiest, so I'm going to use that one. I'm going to solve for x, and we could say x is equal to y. Is that clear from the second equation? Just divide by 2 and move the 2y over. And then we just plug in. Okay, and at the same time, I'm going to divide the first equation by 2. So notice we have y minus x minus 5 is equal to 0. So now we plug in x equals 2y. So we got y minus 2y minus 5 is equal to 0. Or negative y equals 5 or y equals 5. Y equals -5. Any questions so far? Okay, so if y is -5, then x is 2y, put that in the same line. So x is equal to negative 10. Is that clear? Okay, so that's the location of the maximum. So we found the location. So the location of the peak is at negative 10 comma negative 5. And the peak, the elevation is, and now what I'm going to do is I'm just going to copy, I don't know if I can copy. Yeah, I think it lets me. Well, maybe it doesn't. There we go. Just so I have it in front of me. It's already off the page. So we have that function. And what we're going to do is now we're just going to plug in the x is negative 10, y is negative 5, and you get 2 times negative 10 times negative 5, which is 100, minus x squared, which is 100, minus 2y squared. Y squared is 25, so that's minus 50. And then minus 10x, so that becomes a plus. 10 times 10 is 100, plus 10,000, and that's 10,050. Any questions on that? So could be basically down to Lac. It's about the same elevation-ish. Any questions at all on this example? It's kind of the longest problem. There's nothing that should have been tricky about it because it just asks you to do the gradient, all the stuff with the gradient that we did. Okay, there's a lot with the gradient. Okay. So the next question, use a spherical coordinate formula. I decided to give it to you because it's kind of messy and I didn't feel like I should make you have it memorized. I didn't want that to be the error, but I want you to know how to use it. Part A is use the chain rule formula for spherical coordinates for the derivative del f del rho. And notice on part A, we don't know f. You can't use B to do A. This is in order. Okay, A always comes before B. So what I'm going to do is I'm going to use the partial derivative formula. Okay, and I think this one I'm going to need to go this way. So del f f. There we go. So del f del rho there's the rho is equal to, and I think I'm going to use the other notation because it's easier. That's going to be f, the partial derivative of f with respect to x times the partial derivative of x with respect to rho. And then plus f sub y times y sub rho plus f sub z times z sub rho. And that is fx, which we don't know. Okay, again, this is general. X rho we do know because x was rho times the sine phi cosine theta, so it's just sine of phi times the cosine, one more time, times the cosine of theta. And then plus, then f sub y. And then y, same idea, except instead of rho sine phi cosine theta, it was rho sine phi sine theta. Let's copy and paste it. And then plus, and then f sub z times, and then remember z is rho times the cosine of phi. So cosine of phi and phi. Any questions on part A? Any questions? This is just applying the chain rule. There's nothing special here, but you got to be able to do it. That's all. And then part B is consider the function. Let's copy and paste it so I don't lose it. There's our f. Let's find del f del rho. And it says you don't have to simplify it. Okay, you just can't have any derivatives written in. So for B, let me just do that so I've got it. So what I'm going to do now is I'm just going to have this guy, and f sub x now is just 2x times sine theta. I think I'll just type it out. Sorry, sine phi cosine of theta. And then f sub y. F sub y is going to be the derivative. So that's the derivative of the cosine of y is the sine, is negative sine of y. So the negatives go away and you get z sine of y times sine of phi cosine of theta. Wait, just a minute. Times sine of phi sine of theta is what I meant. And then finally, plus f sub z, and f sub z is cosine y times cosine phi. And that's it. Okay. Again, I didn't ask you to simplify it. I just want to make sure there's no derivatives when you're done. And there's no derivatives. You don't have to substitute the x and y in there. Any questions at all? Any questions at all on this question? Do you agree it's easier to watch than to do?
Yes.
I'm not doing anything fancy, am I? But that doesn't mean that it's easy for y'all. I mean, I understand this is tough. Okay, consider the surface. This guy, find the angle between the tangent planes to the surface at the points 1, 2, 2 and 0, 1, 5. And I gave you a hint because I was worried if I didn't give you a hint, I didn't know if anyone was going to get it. So the hint, first find the gradient at the 2 points. Let's do it. Grad of f. Okay, I just write grad of f and then I'll plug in. And the derivative with respect to x is 4x. The derivative with respect to y is -1 plus z. And the derivative with respect to z is just y. Any questions on that? Okay, so now I plug in. Grad of f of 1, 2, 2. And when I do that, x is 1, so I get 4, comma, -1 plus z, z is 2, and that's 1, comma, and y is 2. And then grad of f at the other point, 0, 1, 5. And if we plug that in, then if we plug in x equals 0, you get 0, comma. If you plug in z equals 5, you get 4, comma. And if you plug in y is equal to 1, you get 1. Any questions at all on finding the gradients at the 2 points? All right. So I asked you for the angle between the planes. I did not ask you for the equation of the plane. But the idea is that we have the gradients, which are the normal vectors for the 2 planes. So if you remember, the definition of the angle between the planes is you just find the angle between the normal vectors. So how do you find the angle between the normal vectors? The hint is there's an easier way and a harder way. What's the easier way? And some of you did it the hard way, by the way. I won't mention names. That's the easy way to find the angle between 2 vectors. Yeah, we have a formula, and it's the dot product formula. Again, the cross product formula will still work. That's a lot harder. So why torture yourselves? Let's do it the nice way. Okay, this isn't supposed to be tricky. This was a standard formula we had for angles. Just there are a lot of little details in the first, part of the class. There's fewer details in the second part of the class, but the bad news is lots of proofs. So it's harder thinking, fewer things to think about. So I don't know, most people find proofs hard. All right, so let's find the dot product. So if you take the dot product, that's going to be 4 times 0 plus 1 times 4 plus 2 times 1, which is, how about 6? Is equal to, okay. So that's our dot product, okay. And that's supposed to be equal to, so you didn't really mean V dot W, you meant magnitude of V times the magnitude of W times the cosine of the angle between them. So we can take the magnitude of 412, and that's 16 plus 1 plus 4, which is 21. Times the magnitude of the second vector, which is 0 plus 16 plus 1, which is 17. And I guess I need to put some square roots in there. And what I'm going to do is I'm going to note that we're taking square root of each, so you can take them combined. So square root of 21 times 17. And then times the cosine of theta. And then we just solve for theta. And theta is going to be equal to 6 divided by the square root of 21 times 17. And that's it. Any questions on 7? Okay, let's get to number 8. Okay. Write down an example of an equation that produces a hyperboloid of 1 sheet. So how many minuses must there be? How many negative signs?
1.
1, and everything needs to be squared. So how about x squared? Where'd it go? One more time. X squared plus y squared minus z squared is equal to 1. That's part A. Okay, there are a lot of good answers for part A, but you needed to have everything squared. You can't have 0 on the right-hand side, and you have to have 1 negative. Okay, and then part B, it's got to remember name of the quadratic surface. Notice, by the way, if you let z equal 0, you get y equals x squared. That's a parabola. If you let y equal 1, you get an ellipse. This is an elliptical paraboloid. And that's it. Any questions on that? This is kind of all or nothing. Not a trick question, but just got to remember the language. Okay, use Lagrange multipliers to find the point on the plane closest to this point. Okay, I actually made a mistake on this one. It turned out I didn't need to change it because of the way because of my mistake. This problem was a lot easier than I expected it to be in terms of numbers. The bad thing is most people didn't even like get to that point. Okay, so we'll see that in a minute. Okay, but I did tell you must use Lagrange multipliers. And the first thing is closest. That means closest distance. So what is my function that I want to minimize if you want it to be closest? That's what most people have trouble with. So if you want to be closest from the point to the plane, so a point on the plane that's closest to this point, and I want to be closest, what's the function I want to minimize? What measures how close something is? Yeah, distance formula. And I did an example in the lecture. The square of the distance, you don't have to worry about the square root. So I'm just going to use capital D for the square of the distance. And that's just going to be the x minus 1 squared, because we're from the point 1, -1, 1, plus y plus 1 squared, and then plus z minus 1 squared, because that'll be the distance from a point to 1, -1, 1. Okay. So now what we do is we take the gradient of our d function and we set that equal to lambda times the gradient of the plane, the constraint function. So that's going to be 2 times, sorry, with vector. So 2 times x minus 1, comma 2 times y plus 1, comma 2 times z minus 1 is equal to lambda times 431. Any questions on how I got 431? It's like one of the easiest gradients you can imagine. Any questions on that? Okay, so now what we can do is we can write down the equations. We have 2 times x minus 1 is equal to 4 lambda. And I'm just going to use L for lambda, less typing, capital L. And then we have 2 times y plus 1 is equal to 3 lambda, or 3L. And then we have 2 times z minus 1 is equal to L. Any questions? Okay. And then we also, by the way, have 4x plus 3y plus z equals 2. So those are our 4 equations, 4 knowns. Okay, this wasn't supposed to be that evil, even though it's a little tough, but it's not so bad. So there's lots of ways of doing this. Okay, one way is saying, well, lambda is 2 times z minus 1. So whenever you see a lambda on the first 2 equations, write 2 times z minus 1. That might be the easiest way, is we've got lambda. So we can say 2. Okay, and then at the same time, notice there's a 2 everywhere. So I can get rid of those 2's. So get x minus 1 is equal to 4 z minus 1. And then we also have y plus 1 is equal to 3 z minus 1. Any questions so far? Okay, let's solve for x and y in terms of z. So we get x. In fact, I'm going to copy and paste, it's less typing. So x equals 1 plus 4 times z minus 1, and y equals -1 plus 3 times z minus 1. Okay, now I can take the x and y equation and put that into my constraint equation, and we get 4 times the x plus, and then we have 3 times the y. And then we have plus z equals 2. Any questions on that? Okay, now it's just kind of messy. And I don't think I'm going to waste your time in like multiplying this out. It's just very, very basic messy algebra. And what you end up with is z equals 1. But then if z equals 1, now we go back where we had our x, y, and z in terms of z, x and y in terms of z. If we take 1 plus 4 parentheses z minus 1, you get x is equal to 1. And then if you take y equals -1 plus 3z minus 1, you get y is equal to -1. So notice the point is 1, comma, -1, comma, 1. So anyone see where I'm kind of made a mistake in running this test? I'm making it a little too easy. I actually had a typo, but the typo made it easier for you, not harder for you. So that's why I didn't retract it or anything like that, because it wasn't wrong or anything. No one noticed? I don't see y'all jumping in. So I want to use Lagrange multipliers to find the point on the plane that's closest to this point. Well, this point is on the plane. So obviously, if you're on the plane, you're closest to yourself. Does that make sense? I don't think anybody noticed it, which is kind of funny. Any questions at all on this problem? Question 9? Okay, let's look at question 10. Okay, consider this curve, x squared plus y squared minus x, y equals 4. A is convert to polar coordinates. Okay, so some of you actually, it's correct, but harder, is you substituted x equals cosine r cosine theta and y equals r sine theta into all the x's and y's. But what's the easier way of doing it? What do you notice? Yeah, x squared plus y squared is r squared. This is r squared minus xy, which is r squared times cosine of theta times the sine of theta equals 4. Okay. And by the way, you could either do it in part A or part B. I might as well do it in part A. Let's solve for r. So if you solve for r, you can factor out an r squared, divide, take a root, and you get r is equal to the square root of 4 over 1 minus cosine theta, square root of 1 minus cosine theta sine theta. Oh, actually, I did that square root. So I want to take a square root and say that's a 2. Yeah. Any questions on part A? Okay. And technically it's plus or minus. So if you want to write plus or minus, you can. But I didn't take any points off if you didn't write plus or minus. Okay, part B is just a, part B is just a formula. It's not that hard, but you did need to use it. We had a section on it. And that was 1/2 times the integral from the low to the high. Some of you forgot the bounds. If you're in the first quadrant, what are the bounds?
0 to pi over 2.
Yeah. So it's 0 to pi over 2. And then what's the integrand? Once you pull the 1/2 out.
R squared. dx.
Yeah, it's r squared. And r squared is going to be 4 over. And let me just copy all this. The square root goes away, which is a nice thing. D theta. And that's it. That's all of part B. There's not much work. There's no work to show. You just plug it in the formula. Okay. And then again, I decided to not make you do the integral because that would have taken too long. But that's something you learned last quarter, is how to integrate something like that. It's a bit messy. Any questions on number 10? Okay, we're getting there. Okay, please answer the following true or false. If false, explain why or provide a counterexample. If true, explain why. Okay, so the first thing, by the way, I want to focus on that word there and that word there. No matter what, you need to explain. Okay, you can't just say true or false. That's not enough. The whole point is the explain. Okay, and you have good explanation. So for any two vectors, v and w, v cross w dot v is equal to 0. So what is the direction of v cross w? If you take a cross product of two things, what do you know about that vector in terms of its direction?
It's orthogonal to those 2 points.
Exactly. So let me just write that down. So note that v cross w is orthogonal to both v and w. In particular, and let's call this, how about n? It's a typical letter for that. N is orthogonal to v, right? If it's orthogonal to both, it's orthogonal to v. That's all we care about. Why is that good? If it's orthogonal to v and you take a dot product of v, what do you get? Yeah, exactly. Orthogonal vectors always dot to 0. So true. Any questions on this question? The harder way of doing it is to actually say, well, let v be a comma b comma c, and then w be d comma e comma f, and actually grind through this. What I found is that those people who did the grinding through, more than 2/3 of them made a mistake somewhere and thought it was false. Because if you make a mistake somewhere, you're not going to get 0. Okay, somewhere, some arithmetic or algebra thing. So grinding through is much harder, and also usually going to end up with the wrong answer because there's so many little things to do. It's easy to make one little mistake. Whereas if you understand the geometry, it's immediate. Any questions on question 11? Okay, let's go to question 12. This is our last real question on the test. If f of xy is a differential function such that all of its level curves are parallel lines, then the surface z equals f of xy is a plane. Okay, And the idea here is if we think of, say, z equals x plus y, there's a lot of examples, by the way, squared. Then notice the level curves are some constant c, because remember you set z to a constant, equal x plus y squared, or x plus y is equal to square root of c. And remember, c is a number, square root of c is also a number. So y is equal to negative x plus the square root of c. Okay, notice no matter what c is, the slope is always -1. These are parallel lines with with slope -1. Different y-intercepts, but that's okay. But z equals x plus y squared is not a plane. Okay. Any questions? In fact, what is z equals x plus y squared in one word? That's the p. But it isn't a plane, by the way. You want to see? It's a paraboloid. Okay, it's a paraboloid because you have that square there, but it's definitely not a plane. One of the definitions of a plane is the partial derivatives always have to be constants. And this time, the respect to x or y is not a constant. Any questions at all? Any questions at all on question 12? Okay, question 13, which everybody did, which is good. We don't have any foolish people in the class because there's no reason to lose points because all you do is say something. I want to mention a little bit. First thing is you got up to 15 points. The only reason why you got less than 15 is if it brought you to 100%. And then you better smile. Okay, but most people needed the points. So that's one thing. In terms of things you want changed, there's some things I can't do much about. We have to have a proctor test, and Proctorio really is the only software out there that we've got. Otherwise, it's very expensive, and I won't do that to you. It's our college's it's not quite policy, but kind of like policy, that if we're using proctor test, we got to use Proctorio. So sorry about that. I would love to get back. Did you read the news today? This morning?
Not yet. What happened?
The human trials worked. So that's a good sign. They have a vaccine. It was a drug company in America, actually, and the human trials worked. So there is hope. I like hope, don't you? So they did a sample size of 45, which is not high enough, by the way, statistically speaking. For those of you who have taken my stats class, know that if you have a yes/no question, yes, you got it, no, you didn't, 45 not big enough. But at least it's a start. And they found everybody was resistant. Okay. Once they got it, everybody had the antibodies once they got the vaccine. So let's hope. Okay, I want to get back as much as you guys do. Okay, so I can't do much about that. Sorry about that. I wish. I'm a math guy, not a drug person. But hopefully those people will make it work for us. The thing is, there are a whole lot of you that wanted more of, and then you say the next one. And the problem is, whatever I do more of, I have to do less on something else. So sorry about that. So that's the hardest thing. Factorial was a kind of, I wouldn't say universal, but the one thing that more people didn't like than the rest. Some of you want more examples, like the homework. And also we're upset that the quizzes are different than the homework, okay? Quizzes are going to be different than the homework because they're different. The main thing between the quizzes and the homework is the quizzes are graded by me and the homework is graded by a computer, okay? And people are smarter than computers so far, which means that I can use the quizzes to have you write stuff out and then read it, which is what the tests are going to be like. I have to give you the quizzes different than the homework. So sorry about that, but if I didn't give the quizzes different than the homework, you get killed on the test because you'd have no practice because the tests are more like the quizzes. Did it feel like the test was like the quizzes?
Yeah.
Yeah, I did. The tests are like the quizzes. I can't make the homework like the quizzes because it's computer graded. Okay, so that's the whole point of having quizzes every day. Except today, by the way. No quiz today, obviously. Sorry about that. I can't make them the same. Any questions on that?
I don't think the concern was about them being the same. I think it was about them like correlating to the homework, and some of them don't really seem to do that.
They do, but what you need to do, whenever, you notice I always start the class? How do I always say, what do I always start with?
Plan.
Are there any questions?
No. Yeah.
Usually before the plan, right? Sometimes right after the plan, but sometimes before the plan. And if you have questions, I can answer them. The other thing is after class, I always have office hours. And guess what I do in office hours?
Well, I feel like maybe you should make it a little bit easier so that like you answer our questions during the lecture rather than after or before.
I will answer. You just have to ask. Do you see? You could ask anytime. If you ever have a question, ask and I'll go over it. Okay. But afterwards, I have a whole hour of doing it. And I did notice it helps to come to office hours and ask questions because those who did well on the test. Okay. So again, ask questions and then I'll answer them. Does that make sense?
Sure.
I'm about to go over homework unless there's questions. And if there's no questions, you got it. And if you don't, then I'll be happy to answer questions. Okay, just like I did in class when we had face-to-face class. It's just you tended to ask a few more questions. Okay, so that's the main stuff. The thing you liked was the quizzes. More people like the quizzes than anything else they said they liked. And there's a lot of things I can't do anything about. I'm just hoping for this vaccine so we can get back to normal next, maybe fall, but they're thinking winter, but I don't know. The sooner the better is my feeling. But there wasn't like one overwhelming thing except Proctorio, and I can't do anything about it. I can't do a no Proctorio test. It doesn't work. I will tell you, this morning, yesterday, 4 times, the day before, twice, every day, I get questions from students that are clearly from their exams. Not my students, by the way, but students that have take-home exams. And I don't answer them, but I know they'll find someone. My daughter will answer them. She gets paid. She does that for a living. She does mostly Japanese, but she'll do math too. So with take-home exams, you can just pay. And I don't believe in letting you do that or, letting the rich people get in and pass and the poor people can't pass. I think that's wrong. So just a note, a few things. Any questions about the test before we say goodbye to it? Any questions? Okay, let's say goodbye. It's past history. We won't go back to it basically until we start talking about the final. The other type possible thing is application presentations. So I want to show you the schedule. So we are here in week 7. And notice in week 9 are your application presentations. Okay, I didn't really talk about them, but now is the time because now you want to start thinking about it. You still have a few weeks, but these are group projects. You could have 2 or 3 people per group, and you're going to give a oral presentation where you share your screen. Got it? And you're going to have 5 minutes to show an application. And it could be anything from this class.
Does that mean just this quarter or
Yeah,
any
this
of
quarter.
them? Okay.
Yeah, this quarter. So multivariable calculus, or the stuff we haven't done yet, which we will soon, which is series and sequences. But there's more multivariable calculus applications that you'll understand anyway. Okay, and we've had a bunch. I will show you, and if you want, I can pop it in the spreadsheet. This is I don't know if I've shown you this particular page before. These are the videos, and by the way, unfortunately, I can't do the videos on Zoom. It overloads my internet, and then it won't work. So there were a couple people that wanted the videos. I can't do it just for technology purposes. I have the videos. But these videos will give you applications. That's one thing. If you want some applications, the book has a bunch also. Internet has over 1 million. But I also created these videos. I didn't create the videos. I cataloged videos of courses that weren't math, that use math. This is where all of my applications that I did in class last quarter. And they started, so it's all of this. Okay, and by the way, this isn't one video each. If you go to, say, Lagrange multipliers, that's the last one, you'll see a bunch of Lagrange multipliers examples. Okay, so those are ways of finding examples. I'm also happy to help you. If you can tell me what you're interested in, I could probably find something for you. But you need to work in groups. Okay, any questions on that? We'll talk about it later as it goes too. Okay, let's get to new material, which is here. Okay, and I'm going to say new material. Most of it's not new material. Most of it's pre-calculus. Okay, so first thing is, what is a sequence? Yeah, you had it in pre-calc. What does it mean to say I have a sequence? Any ideas?
I want to say a set of numbers.
Okay, a set of numbers, a list of numbers. Okay, I'm gonna give you a little bit more mathematical definition. It's the definition that uses the most important thing there is in all of mathematics, which is?
It's either going to be
I like what
the
Victor said.
Pythagorean theorem or
Functions.
functions.
I've said that lots of times. That that might be my bent, but we talk about functions everywhere. Let me write that down. Definition. A sequence is a function. Now, if I say that it is a function, what do I have to tell you? What 3 things do you have to know to understand that it's what it is? Yeah, we gotta know the range, the domain, and the rule. Okay, so a sequence is a function whose domain is the whole numbers, and the range is the real numbers. Maybe I should say is a subset of the real numbers. And that's the definition of a sequence. So, yeah, you could say it's a list of numbers. I mean, there's other ways of talking about it, but there's a math class, so I figure I should do the definition, the math definition. So, like, if you say it's a list of numbers, that means that I could ask you, what is the 7th number in your list? That's the same thing as what is the function evaluated at the number 7. Do you see that? And what will you get? You'll get a number. Any questions on what a sequence is? Okay, well, it turns out there's lots of ways of thinking about sequences. And by the way, we're going to spend the entire rest of this quarter on sequences. That's all we're doing. There's a lot involved in it. So today is just intro on what a sequence is. And then what we're going to do basically from tomorrow, Wednesday on is adding sequences, taking sum of sequences. But today we're going to stick to, this is just a sequence. So let me give you an example. How about 3, 6, 9, 12, 15, dot, dot, dot. And I'm going to write down a sub n. That's the standard notation. We tend not to use f for a sequence because that sounds like your domain are real numbers. We tend to use a sub n, because n looks like a whole number, and then and a is that function. So that's the same thing as saying f of n. All right, how do I write this down as kind of, there's actually two ways of writing it down. One is a function of n, where you plug it in and you get a number. Any ideas on that? We had this in intermediate algebra and pre-calc. Good, good, good. This is 3 plus 3 times n minus 1. Okay, this is called the explicit format. Okay, I'm just going to write explicit. So it's the explicit way of writing a sub n. Okay, any questions on that? What's nice about it is if I told you n is 100, then you could just do this. And you'd say 300 because you plug it in. So explicit is really nice. Sometimes you can't do explicit, but you do what you have to do. There's another way of writing sequences, and that's called recursive. So in that case, what you do is you say, what is a sub n plus 1 based on stuff before it, in this case, a sub n. Okay, so what we can say now is a sub n plus 1 is equal to, well, what do? You just add 3. A sub n plus 3. But you also have to say how you start. And I'm going to start at 0. There's actually 2 ways of doing this. And I'm going to divert a little bit from the book's way. I'm going to say our first number is 0. Okay, our first count is 0. And there's 2 reasons for that. So a sub 0 is 3. Also, because the first number is 3, and you keep adding 3s. Okay. Who knows why I like to start at 0 instead of 1? Call 0 the first element instead of 1. Any thoughts? Yeah, 1 is for computer programming. So if any of you have done any coding, you always start at 0. But more importantly for this class is we're going to have a whole chapter. We have 2 chapters left, by the way. And the second chapter is all about Taylor polynomials and power series. And they always start at 0. Okay, or just about always. So I want to get you used to it. So that's the main reason. And it's good to learn how to program computers too. So it may feel a little weird that your first number you're going to count from is 0, but it's just the way it's done. Any questions on this?
I have a quick question.
Uh-huh.
You said we're going to be dealing with sequences and series for pretty much the remainder of the quarter.
Yep.
Is that limited to specifically arithmetic, or are we going to add geometric in there as well?
Oh, it goes on and on and on.
Okay.
It's not just arithmetic. It's not just geometric. Just because the first example I gave is arithmetic doesn't mean that's all we do.
I had a feeling. I was just curious.
Oh, no. We're going to do lots and lots and lots of sequences. No. For example, we're going to have a sequence for sine of x. You know, if you want to say what is a sine of 0.1, there's a sequence for that. Okay, we're gonna have a sequence for anything. Okay, and just trust me on that. Sound good?
Yeah, sounds good.
And if you do sine of 0.1, it's not arithmetic, it's not geometric, it's gonna be something else. And we'll learn about it. So, but right now you just gotta trust me that this stuff is very important. But the first week or two, you're not gonna see it. You're not gonna see a lot of applications. We're just gonna do a lot of learning machinery, and then we'll start using it later. All right, so let's go to another example. Since you said it, let's suppose we had, I'm going to do a variable instead. So a sub n is equal to x, comma, x squared. In fact, let's do it differently. Let's go 1, comma, x squared. Comma, x cubed. Maybe I'll even do it a little bit differently. How about 2, comma, 2x squared, comma, 2x, comma, 2x squared, comma, 2x cubed, comma, dot, dot, dot. All right, so this is going to answer your question right away. Are we only going to do arithmetic, or are we also going to do geometric? Well, what do you think?
Yes.
Yeah, this is geometric. So again, this is f of x. This is equal to, now we can write this as a function, and we write this as 2 times x to the n. Okay, and again, n starts at 0 here. Okay, you could also do this recursively. And we can say that a sub n is equal to 2x times a sub n minus 1. That's right, it's just not 2. It's just x times a sub n minus 1, comma, a naught equal to. So again, explicit and recursive. Okay, let me give you another one just for fun. How about a sub n is equal to 2, comma, 7, comma, 1, comma, 8, comma, 1, comma, 8, comma, 1. That's right. 2, comma, 7, comma, 8, 7, comma, 1, comma, 8, comma, 2, comma, 8, comma, 1, comma, 8, comma, 2, comma, 8, dot, dot, dot. Is that a sequence?
Yes.
Okay, yeah, that's sequence. Okay, what is a sub 10?
One.
Does everyone agree it's 1? What do y'all think? I don't see y'all jumping in. Okay, it's not 1. It's 4. Anyone know why? Very important sequence. I don't see everyone jumping in. I'll write it a little differently. Yeah, T. Okay, so sequences don't have to be geometric. They don't have to be arithmetic. This sequence is a very important sequence, right? It's a sequence of digits of E. Okay, and hopefully you know in calculus that was a pretty damn important sequence, right? Okay, and again, it may feel like a 1 next. It feels like a pattern, but actually he doesn't have a nice pattern. Okay, but an important number. Any questions on this example of a sequence? There's other sequences. I want to give you another one that's important that comes up in lots of applications that you might have seen before. And let's write it out. I'm going to write it recursively. A sub n is equal to a sub n minus 1 plus a sub n minus 2 a sub 0 is equal to a sub 1 equals 1. What sequence is this? I bet you've all seen it before.
Is it binary?
No. It's not a math word when you're going to say it. It's a word, but it's not a math word. It's a person's name. That's a hint. Last name. There we go. Yeah. It's a Fibonacci sequence. This is a Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, etc., etc. And that's a Fibonacci sequence that comes up all over the place in just nature. It's kind of cool. So that's a recursive sequence. And I'm not going to do this today. Might do it next year. And that is, how do you come up with the explicit formula for the Fibonacci sequence? Okay, and again, we're not going to do that because it's too hard. But next year, there is an explicit sequence, but you have to truly understand matrices. I know it doesn't feel like matrices, but it is. Okay, so again, I wanted to introduce, again, today is day 1 of the rest of the course. So I want to make sure that you kind of have some good ideas of sequences. Okay, there's a lot of other sequences that are really important, which we'll get into as the quarter goes. All right, so the next thing you want to say, which none of these have, is, does a sequence have a limit? So can you find the limit of a sequence of numbers? So let me give you an example. Okay. Okay, so online encyclopedia of integer sequences. Okay, again, online's got everything. Sure, there's a zillion examples, and I probably know some of them online, but I don't know everyone probably. But let me give you another example of a sequence where we can talk about a limit. How about, this is an important one, a sub n is equal to 1 comma 1/2 comma. We said we can think of it as a function, should have a limit, I think. No, not all. No, that's not true. None of the ones I've given, are have limits. And we haven't defined it yet, so you don't know what a limit is, but we will get. But I wanted to show you one that does have a limit. 1/4, comma, 1/8, comma, 1/16, comma, ... Hopefully you can see the pattern. This one has a limit. Okay, what happens? N gets very, very, very large.
We go to 0.
Yeah, we got a 0. You can see a limit. Do you see that? On the other hand, none of these other ones, the first example goes off to infinity. Do you see that? If n gets very, very, very large. Okay, the second example might have a limit, might not, depending on x. If x is not 0, if x is 1 or bigger in absolute value, then it has no limit. If x is, it turns out, smaller than 1 in absolute value, it does have a limit. The third example, definitely no nice limit. Okay, if you ever ask what is the last digit of e, yeah, right. Does that make sense? Okay, it doesn't just become something. Okay, but this last one does. This has a limit. So let me write down the definition. And that is the limit as n approaches infinity. We always do infinity, by the way. Of a sub n is called the limit of the sequence. Okay. Now I'm going to say that the formal definition, you're not going to do much with it, but I should say it just so you get used to it. And that is a limit as n goes to infinity of a sub n equals L. If, given epsilon greater than 0, there exists a capital N, such that if lowercase n is larger than capital N, then the absolute value of a sub lowercase n minus capital L is less than epsilon. Okay, I'm not going to test you on the epsilon n definition of a limit, but it's good for you to have heard it. I don't want to get fired, so I'm supposed to tell you that if I don't say the definition, then I'm not doing my job. Okay, but if you want to really learn about the formal definition and really work with it, you need at least 2 more years of math, and you'll get there. Right now, I want you to get the idea of the limit, and that is, you can look at this last one as like, yeah, that one goes to 0. Whereas the E sequence does not converge to anything nice. E doesn't converge, doesn't all of a sudden become the same number. Does that make sense? Neither does pi, by the way. Okay, there is no last digit of pi. Okay, you can't, it just doesn't all of a sudden become the same number. So forget it. Okay. Any questions on that? Any questions? Okay, so let me get on to my agenda. So we talked about a limit of the sequence. Let's talk about limits and functions. This is a theorem, and it's a nice theorem. And it says the following. let f of x be a function such that f of n is equal to a sub n for every large n. Okay, and when I say large as you want it to be. Okay, so in other words, if it doesn't agree in the first 100, but then after that it agrees, good enough. So eventually it has to agree. Okay, and then from then on, it has to agree. Then if the limit as x approaches infinity where is that arrow? That one. Of f of x is equal to L, then the same is going to be true. Then the limit of a sub n is also L. Any questions on the theorem? Okay, so let me give you an example of how you might use this. Let's suppose a sub n there we go. Just want to make sure you can see everything. Let's suppose that a sub n is equal to sine of 1 over n times n. So what is the limit of a sub n? Well, how do we do this?
We think about it first. What happens when we plug in for n?
You could do that and you get infinity, right?
Mm-hmm.
Times 0.
Yeah.
And that's a problem. You
Yeah.
guys want to plug in and see what happens, but that doesn't help. Do you see that?
Yep.
Here's a hint. What did I just do before this example? It's still on the page. Yeah, we use a theorem. Okay, that's the whole point of this example, is to show you how this theorem is used. So let f of x equal x sine of 1 over x. Any questions on that? Which, by the way, is equal to one over x. Let's go, that's right, sine of 1 over x over, I don't think I can do it this way. Try, I don't think so. Oh yeah, it did let me do it. Over 1 over x. Do y'all agree that's the same thing? Okay, well, if we have that, notice, by the way, obviously f of n is an. Are you convinced of that? If you plug it in, you get the same thing. You get an. Okay, well, the limit as x goes to infinity of this function is the same as the limit as x goes to 0. Of the sine x over x. Just a little substitution. Do y'all agree? You can think of letting u equal 1 over x, and then it just becomes this. What is that limit? Yeah, you could use L'Hopital's rule and say that's cosine of x over 1. Cosine of 0 is 1. So therefore, by the theorem, the limit of an is 1. Any questions on that? Okay, so that's one way of finding a limit, is if you can find a function that agrees with the sequence, then you can use calculus. Any
So
questions? Yeah.
how did you get the trying to find the right way to say this. How did you get the justification to make it sine of x over x?
Okay, so maybe it'd be helpful if I did it this way. Maybe it'd be less confusing. The letter doesn't matter, but maybe if I call it u instead.
Okay, that makes sense.
Where u is 1 over x.
Mm-hmm.
And notice if x goes to infinity, 1 over x goes to 0. So u goes to 0. So good? Yeah, so it's a trick. It's a classic trick in limits. Bruce probably showed you a long time ago, but a long time ago is a long, long time ago. Okay, so let me just show you. We've done it, limits. I'm just going to say the limits in algebra, and the idea, what I'm going to tell you is everything you did in calculus still works. So remember that if you have a limit of two functions and you add them up, you get the sum of the limits. Do you remember that? Same thing with the difference, same thing with the product, same thing with the quotient as long as the denominator is not 0, same thing with the function. So I'm just going to say all that because there's not much to say there. Just do what you expect to do. Is that clear? So that means you can split apart pluses and minuses and times. Okay. The squeeze theorem is also a quickie, same as the same squeeze theorem in calculus. That says that if you're in between two different functions, you're above somebody and below someone else, and both of those people go to the same number, then you're going to that number. Does that make sense? So that was a squeeze theorem, and it's no different. That's why I'm not spending much time on it, because you had that in first quarter calc. You had the squeeze theorem. So it's the same squeeze theorem. I do want to spend the next few minutes talking about bounded sequences, and then monotonic and the monotone convergence sequence. So first thing is definition. A sequence is called bounded if there exists, maybe I should say a sequence AN, just so I had to refer to it. If there exists an L with the absolute value of an less than L, or all in. Okay, it's what you kind of think in pictures is it doesn't go above a certain, you can grab a wall above and below, and you're never going to get above and you're never going to get below that wall. Okay, and you can always let the wall be the same height above and below in that way, say. So that's the definition of bounded. And then now the definition is a sequence is monotonic if it is either always increasing. I could say, actually, let's go either never decreasing, or it is never increasing. So let me give you some examples. So an example is, let's let an equal 1 over n. Let's go n plus 1. Okay. Is this bounded? What do you think?
Yeah.
Yeah, because notice that if n is 0, by the way, it's 1. After that, it gets smaller and smaller and smaller. Right? If n is 1, it gets a half. N is 2 is a third. N is 3 is a fourth. So it's bounded by 1. And it's never negative, so you don't have to worry about the absolute value at all. Okay, is it monotonic? What do y'all think?
Yes.
Yeah. As n gets bigger, then an gets smaller, always. So it never gets bigger. Any questions on that? Okay, so here comes the theorem. And that is a bounded monotonic sequence converges. So if you have a sequence and you can show that it's bounded and it's also monotonic, then it must converge. I don't have time to prove it, but you can imagine if you have a sequence and it never gets high and it never gets low and it always goes in the same direction, it can't jump up and down like erratically because it never goes up and down. And it can't go up forever and keep going up really high. It's got to eventually stop going up much or stop going down much because we have that bound that keep you from going up too much or down too much. Okay, so that's kind of the idea of the proof. The proof involves, you know, the full epsilon delta, epsilon n stuff, which I'm not going to do. Any questions on this theorem? So if you can show a sequence is bounded and monotonic, then it converges. So what about our example? Does that converge?
Yes.
Yeah, because it's bounded and monotonic. Converges. Okay. Yes, you can turn it into a function. You go f of 1 plus x. F of x is 1 over 1 plus x, and take a limit. But sometimes it's easier to just say it's bounded and monotonic. Done. Any questions at all on bounded and monotonics, and as we call the bounded monotonicity theorem.
I have a question, but not necessarily related to monotonic.
Sure.
Do you mind going over what it means to be convergent or divergent again?
Okay. So convergent, so let me go to the definition. So convergent is the same as we had with improper integrals. Is that it converges if the limit exists, diverges if the limit doesn't exist.
Okay, that makes sense.
That's it. Yeah.
Mhm.
So it's the same word we had last quarter. That's why I didn't do much with it. Maybe I should have. I was also running out of time because we had to take a lot of time on the test. Okay. We are, class is officially over, but I am always happy to help you out. It's office hours.